Hey class, so here is my first screencast video that I'm making for you guys since class was canceled today. So I just want to go over the last little bit from chapter 1, which primarily consists of unit conversions and dimensional analysis. Alright, so we're going to start by doing unit conversions, and the reason unit conversions are important is because from time to time you might come into contact with something or a problem that has different units. So for example, let's say you're going down the road at 50 miles an hour and you do so for 10 minutes and you want to figure out how far you've gone. And so you think, oh yeah, I know. Okay, distance equals rate times time. Distance equals velocity times time. If our velocity is constant, so if I went 50 miles an hour for 10 minutes, multiply 50 times 10, 500 miles is how far I went. And you would be wrong, right? You obviously did not go that far because your units did not agree. You had miles per hour and you had minutes. And so you'd either have to convert your minutes into hours or your miles per hour into miles per minute. So that's what we're going to look at doing. So some of you, I'm sure, have done unit conversions. What you're going to do is you're going to take whatever quantity you want to convert, and all you're going to do is multiply it by 1. And when you're multiplying it by 1, what you're really doing is you're multiplying it by some unit conversion. So let's go ahead and look at what this looks like. Again, every unit conversion must be equal to 1. So whatever value is on top must be the same and equal to the value on bottom. So for an example, imagine that you're going down the road at 50 miles per hour. You want to use some of your physics equations, but you like using SI units. Metric system, always better, right? So you want to convert from the 65 miles per hour you're moving to the meters per second, the SI units. To help you with this, I give you some conversion factors that can be found in your book or by just Googling the equalities here. So I tell you that 1 mile is equal to 5,280 feet. That's the elevation of Denver, the mile-high city. And 1 hour is equal to 3,600 seconds, which can be determined by taking 1 hour equals 60 minutes, and 1 minute is 60 seconds. 60 multiplied by 60 is 3,600, and 1 meter is 3.281 feet. So what we're going to do is we're going to take 65 miles per hour and multiply it by 1 3 different times. First, here's the first 2 steps. I ran out of room, so I broke it on 2 lines. But what you can see here is I'm taking 65 miles per hour and I'm just multiplying it by 1 twice. One of the times I multiply by 1 is multiplying by the conversion factor that 5,280 feet is equal to 1 mile. Since they're equal, one on top, one on bottom, what we have is just a value of 1. And what this does, and the reason I oriented feet on top and miles on bottom, is so that my miles, which are on top of my 65 miles per hour, are now on bottom. And since you have something on top and bottom, you multiply and divide by the same thing, they, boom, cancel out. So now we have feet per hour, not what we want. So let's go from hours to seconds. So now, since hours is on the bottom of our original quantity, I put my 1 hour on top and my 3,600 seconds on the bottom. Now my hours, boom, cancel out, and what I'm left with is feet per second. How did I get this value of 95 feet per second? Well, I took my original quantity, 65 miles per hour, multiplied it by everything on top, so multiplied by 5,280, multiplied by 1, and then divide by everything on bottom. So divide by 1 mile and then divide by 3,600 seconds and we get 95. But that's feet per second. We want meters per second. So we need to do one more conversion factor of getting rid of feet and converting it to meters. So you can see here, since feet were on top, I put the 3.281 feet on bottom and the 1 meter on top, took 95, multiplied by 1, divided by 3.281, and I found a box-worthy answer of 29 meters per second. All right, good. So that's unit conversions. Here's another slightly trickier one that maybe you can try if you want to. So gold has a density of 0.698 pounds per cubic inch, and I want you to determine what is its density in kilograms per cubic meter, the SI units. So I'll tell you 2.2 pounds is equal to 1 kilogram on Earth with Earth gravity, and 39.4 inches is equal to 1 meter. So pause the video and try it out. Did you pause? Did you try it? Okay, now hopefully you paused and you got an answer. Let's see if it agrees. So here's my unit conversion. Notice I have pounds per cubic inch, and so I need to get rid of pounds and I need to get rid of inches, not once but 3 times since it's inches cubed. So I have 1 kilogram is equal to 2.2 pounds. Since pounds was on top, I have pounds on bottom, so that those cancel out. Boom. Now I have cubic inches on bottom, so I need inches on top, not once, not twice, but 3 times. So I have my conversion factor for inches to meters 3 times. Sometimes you might write this as just this unit conversion factor cubed, but I don't do that because sometimes I forget to cube my 39.4 and then my solution comes out wrong. So we can see inches cancels out once, twice, 3 times, and what we're left with on the bottom is meters times meters times meters, or meters cubed. So we do the math, 0.698 divided by 2.2 and then multiplied by 39.4 3 times, and you get 19,400 kilograms per cubic meter. And again, that is a box-worthy answer. Cool, so that's unit conversions. Pretty straightforward. You'll get to practice that a little bit with the homework. And the next thing I want to talk about is dimensional analysis. So first of all, what is dimensional analysis even, and why do we care? Well, dimensional analysis is actually a powerful tool to help us make sure that we're using our equations properly, make sure we're using the right equation for the right situation on exams and problem solving and so on. And what it does is it allows us to just look strictly at the units and make sure the units in our problem, in our equation, in whatever we're using, come out appropriately. So for example, let me show you what I mean. I'm going to use L to represent units of length, M to represent units of mass, and T to represent units of time. So let's say we have some equation. Here's an equation. Maybe you're trying to remember this equation when you're doing the homework or something, and you're like, oh, I think there's an equation that says something like x distance equals 1/2 velocity times time squared. So let's use dimensional analysis to see if that could even possibly be a valid equation by looking strictly at the units. So x, displacement, has units of length. 1/2 doesn't have any units, it's just a value, a scalar value, so we don't have to worry about that. Velocity has units of length per unit time, and time, well, has units of time, and it's time squared. So if we calculate this out, what it's saying is units of length must be equal to length divided by time multiplied by time squared. Factor that out, and so we have length times time on the right side of the equation and length on the left side of the equation. Therefore, this is not possible to be a correct equation at all, because the length will never be equal to length times time. You can never have meters equal to meters times seconds. Those units are not the same, therefore that equation is not valid. All right, so let's try an example. All right, one example here. So imagine there's some physical quantity that has a value we're going to call r. All right, and there's an equation where we calculate r. So r is equal to 4a squared divided by b minus c. All right, a is a speed value. All right, so again, distance per unit time. Okay, and b and c are both distances. And so I want you to tell me then, what are the SI units for r? Again, pause the video, try it out, and then we'll check and see if you're right. You better have paused and tried it out. So let's check it. Okay, let's plug in our values. So r is equal to 4, again, is just a number with no units, so we don't have to worry about that. We have a, which is distance over time, or length per unit time, and a is squared. And then on the bottom we have length minus length. So what are units of length minus length? Do they just go away? No. Length minus length, if you have 4 meters minus 2 meters, what do you have left? You have 2 meters. Right? Or 5 meters minus 1 meter, you have 4 meters. So the bottom should just have units of length, and the top would be length squared over time squared. So we have length squared on top, time squared, and length on the bottom. And so you can see one of the units of length will cancel out, and our r should have units of length over time squared, but we are asked for the SI units. So SI units for length are meters, and for time it's seconds. So therefore r should have units of meters per per second. Once again, box worthy. All right, hope that makes sense, and let me know if you have any questions, but that should be a wrap on chapter 1.